All right, let's talk about the scientific method. So here's how you can use this video. If you're using this video to take notes, throughout the screen on the slide there will be text that's highlighted in green. That's the important stuff. That's what you should write in your notebook. There's also going to be blue text throughout the video. That is going to be questions to consider or practice questions. Now also throughout this video there's going to be two codes. One is a written code that'll show up on the screen, and one is a verbal code said by myself sometime throughout the video. They can happen in any order, so pay attention. So let's get started. All right, so let's ask this question. What is the difference between being right and being not wrong? And I put a picture of swans for a reason. So let's just take a look at science, right? The definition for science is a self-correcting process of learning about the natural world through pattern recognition. The human brain is great at pattern recognition. And if you look off to the side, look at the pictures and the number sequences. I just want you to just tell me what patterns do you see? You can quickly start to see some patterns that are going to start to emerge. Now, science operates under the one simple principle, right? It's the principle of wrongness. Science cannot prove anything correct or true. There is a difference between being right and being not wrong. So the example that I use, I put those pictures of the swans up. And if you're in America, all the swans here are white, and every time I see a white swan, that doesn't make me any more right in me saying, hey, all swans are right. I can never be correct in saying that. But if I were to go to a place like Australia, the first time I see a black swan, well, I'm wrong, because now I know that all swans are not white, right? So that's the difference between being right and being not wrong. In science, you are never right. You're never correct. You're just not wrong. Now, let's talk about the difference between a scientific law and a theory. A scientific law is the description of an observed phenomenon and tries to predict what will happen. A scientific theory is an explanation of an observed phenomenon and tries to explain why something happens. So if we're looking at the example of gravity, Newton's universal law of gravitation predicts how mass will attract each other, right? Why the moon orbits the Earth. Now, Einstein's general theory of relativity proposed an explanation as to what gravity is and why masses attract to each other. He proposed that mass warps space and time, and objects orbiting are just falling around the curvature of that space-time. That's the difference between a scientific theory and a law. Now, let's talk about the scientific method, how we get there, right? The scientific method is a logical process that scientists use to investigate questions and solve problems. Now, I put a picture of Galileo up here. Galileo is kind of credited with refining the scientific method as it is now by emphasizing experimentation, observation, and measurement. So these are the steps that he used, right? And every flow chart that you might see out there is sort of just derivative of these, right? It just sort of re-emphasizes these. So recognize a problem, make a hypothesis, make predictions based upon the hypothesis, perform experiments to test predictions, and formulate a general rule. So if we take a look at hypotheses, right? A hypothesis is a testable prediction that explains what you think will happen in an experiment. And it often is written in the format if, then, because. So a good hypothesis is specific. It's written in mathematical terms. There is no ambiguity. So if we look down here at some of these pictures, right? If you say the word large, right? If I'm ordering a large soft drink, you can see in some of these these graphs that large could mean something different. If you look at a different year, notice the large changes, right? If you order a large drink in different countries, you can see, well, that's going to mean something different. But if you say, I want a 32-ounce soft drink, there is no ambiguity. That's what it means by specific. Now, a good hypothesis also explains a wide array of observations. The example that I use is Newton's law of gravitation, right? It described two things, why objects fall down and why, if you look up in the sky, the moon orbits around the Earth. It explains a wide array of observations. And probably the most important thing here is it has a test for wrongness. There has to be a test or a way to go out and test it. So let's just recognize a problem here, right? Does the color of light affect the growth rate of plants? So I want you to practice, what is your hypothesis? And try to follow that if, then, because format. So if we set up this test, what do you think will happen? If, this, then, that, because. Now, Let's take a look at variables. Now we're going to perform the experiments to test our hypothesis. So the independent variable is what is being manipulated or changed. There's only one independent variable, and if we're graphing it, it is going to be on the x-axis, and you can see the graph down here. Now the dependent variable is what is being measured, and there's only one dependent variable. That is plotted on the y-axis. Now constant variables, or you might have seen this differently as controlled variables, those are almost interchangeable, but constant variables are kept the same throughout the experiment, and there are going to be many constant variables. Now if we look at that same problem, right, does the color of light affect the growth rate of plants? So identify the independent variable, dependent, and two constant variables. The independent variable, what we're changing. That's the color of light. The dependent variable is what we are measuring. That is the growth rate of plants. Now the constant variables is everything else, right? We want to keep the same amount of plant. We want to keep the lights on for the same amount of time. We want to water them with the same amount of water, same temperature. Everything else needs to be the same. Now, let's do some qualitative versus quantitative data. So, qualitative data describes qualities or characteristics that cannot be measured with numbers, right? So, when we're collecting data, this is observations and uses descriptive words, color, texture, and appearance. Now, quantitative data consists of numerical measurements that include units. So this would be like measuring and counting mass in grams, time in seconds, temperature in degrees Celsius. So let's just do an example here, right? Part of a geologist's job is studying rocks. So if we look over here to the right, just let's take a look at that qualitative data we could use. If we look at this, like these rocks, how would you describe them? Like that would be like color, shape, like the size, is it big or small? Is it rough? Is it smooth? What does it smell like? These are qualitative data. Now, quantitative data, think about if they put it on a scale. Well, that would give you the weight. That is a quantitative data, a number and a unit. Temperature, that's data. That's a number and a unit. Volume, right? Data and unit. Density, right? These are quantitative data. So let's take a look at some examples here, right? We're going to go through that scientific method. You can see that up here. I have some examples, but I'm going to give you some experiments. I'm going to pause here and I'm going to let you practice identifying coming up with a hypothesis, identifying the independent variable, dependent variable, two constant variables. Then identify examples of qualitative and quantitative data that could be collected in each experiment. So, does the length of the string of a pendulum affect the period of the oscillation? How fast that pendulum goes back and forth? Does the age of a seed affect whether it will germinate or not, whether it will sprout or not? Does giving a car the surface texture of a golf ball affect the car's gas mileage? Does the previous round of Rochambeau, or rock, paper, scissors, have an effect on how people play the next round? And do the actions of flipping and spinning a penny affect the percentages of which side the penny lands? So go ahead, pause this, and get some practice going through the scientific method. Now let's talk about, now that we have quantities, there's two types of quantities that we need to talk about, scalar and vector quantities. Scalar quantities have magnitude only. All right, so the example is like this, right? Mass, time, distance, temperature, and speed. Vector quantities have both magnitude and direction, and if you see them in an equation, they mostly have they usually have an arrow above that variable. So examples would be velocity, acceleration, force, and displacement. And the example that I use, like why it's important, right? When we're plugging these numbers into equations, we need to keep track of the direction, right? Which direction they're moving. Usually denoted by positive or negative. But here's why it's important, right? If you're helping a friend move and you go over and you lift a couch and that friend says, okay, we're going to move this couch 10 feet. Is that enough information to tell you where you're going to move that couch? No, right? You're going to need to know, 10 feet over in this direction. You need to know the direction as well, right? So that's scalar versus vector quantities. Now let's talk about measuring units and how, once we're taking data, how we need to record some of them. So I want you to take a look at some of these pictures to the right. I just want you to say, like, what height do you think this photo was taken from? What would a good estimate be? And if you look at that person, careful, that's me, right? How much does this person weigh? And if you look at this crowd here, right, about how many people are in the crowd, right? If you looked at that person, could you say that person's 181.4 pounds? Probably not, but could you say they're about 180, right? They had a big lunch. You couldn't really say like, oh, like yeah, they're about 181.4, right? But you know about what it is. You know they're probably more than 100, less than 500 pounds. You look at that crowd, you know it's more than 5 people, it's less than 50 million. You have a good estimate, right? Now, in all of these examples, you're doing the measuring. Now, I'm going to ask you, what would you need in order to be more accurate when measuring height, weight, or crowds? You probably need an altimeter, a scale, or like a turnstile, right? So a turnstile is what counts crowds. So they have a better resolution than you. So what a resolution is, the resolution is the smallest interval that can be measured by an instrument. Now, a doubtful digit. It's the last digit in a measurement representing the best estimate or guess beyond the markings of a measured instrument. So this can only be done with analog instruments, not digital instruments. So at this time, I'll go ahead and give you that verbal code. The verbal code is 050. I say that again, the verbal code is 050. All right, now both the resolution and doubtful digits determine the significant figures of a measurement. We'll get to that later, right? So let's take a look at the instruments to the right. Now, I want you to practice what is the resolution and will it have a doubtful digit? So here's an example of doubtful digit if you look down here at the bottom. If you're measuring something with an analog instrument like a ruler, it means it doesn't have a battery in it, right? If I look at that and I zoom in, I could make an estimate as to what the next digit will be, right? So I could say it's 2.1, 2, 3, 4, 5. Well, it's in between 5 and 6, and it's closer to 2.6. So I would say maybe it's 2.58. You can make an estimate. Now, if we look at digital instruments up here, like this stopwatch, well, that does not have that doubtful digit. You cannot make an estimate to the next point. Now, for all of these, right, I'll even help you out with some of these. If we look at this stopwatch, the resolution is 1/100th of a second, right? So that is the last digit, or that is the smallest interval that can be measured by that instrument. So if you want to go ahead, you can pause this, get some practice finding out the resolution and if it has a doubtful digit of these instruments. Now, significant figures. I talked about significant figures earlier. Significant figures are the number of digits in a value, often a measurement that contribute to the degree of accuracy of that value. Now, when you're measuring the resolution of the instrument, or when you're measuring the resolution of the instrument and that doubtful digit determine the significant figures of a measurement. Now, when you're calculating, your result can only be as accurate as the measurement with the least amount of, your least accurate measurement is going to be that. So if you're adding or subtracting, you need to round to the same number of decimal places as the number with the least number of decimal places, right? So it's the decimal places that determine it. Now, if you're multiplying and dividing, you round to the same number of digits as the number with the least number of significant figures. So I'll move this over here. Here are the rules. Like, yes, there's confusing rules. Like here, it's like 0 or, 0 can sometimes be a significant figures. 1 through 9 are always significant figures. We've got trailing and captive and leading zeros. And here's some rules for multiplication, division, adding. But I just want to go through some examples as to why it's important, right? So let's just say you are in a helicopter. And you look at that and you say, oh, it's about 500 feet in the air. So if you take a look at your rules, right, yeah, you could follow this flow chart and you could say, like, oh, yeah, that's only one significant figure. These zeros are at the end of the number. There's no decimal point. They're not significant. They're just placeholders. You are just estimating that. Oh, I'm looking at that. Okay, great. Yeah, it's 500 feet. Now, let's just say you look at the altimeter and it says 503 feet. Well, I have measured all of those digits. Those are significant, right? That 0 there, I measured that, right? It's also the example of saying, if you look at a person and you say, oh, it's about they're about 180 pounds. Well, you made an estimate. That 0 is a placeholder. You did not measure that 0. This has two significant figures if you follow those rules. Now, if they step on a scale and that person, and it says exactly 180.0 pounds, well, If you follow those rules, those zeros, it has a decimal point, those are significant. It has 4 significant figures. But here's how I remember that. I measured that. I measured those zeros. Those are not placeholders. Same thing with crowds, right? You look at a crowd and you say, there's about 10,000 people there. Well, that is 1 significant figure. Those zeros are placeholders. If that turnstile counts as 10,001 person, I measured all of those. In fact, when you're counting and it's an exact number, I think that's what's called like an infinite significant figures, because that's exactly how many people are there, right? There's no ambiguity there, right? But if you looked at that, we would say that's 5 significant figures, right? It's determined by the measuring instrument. Here's also why it's important. If you take a look at this, if you want to find out how fast you are, right? So you and a friend go outside with a stopwatch but forget the measuring tape. So your friend estimates about how far 100 meters is. On your mark, get set, go. You run that length in 13.63 seconds, according to the stopwatch, right? So if you calculate the speed, you get this number. And you're like, well, where would I round to, right? Well, yes, that stopwatch has 2 decimal places. That's the resolution of that. But you do not, your least accurate measurement is you just eyeball how far 100 meters is. So you might be able to say, yeah, your speed is about 7 meters per second, but you couldn't say 7.33. You do not have the resolution. That's the importance of significant figures. Now, let's talk about accuracy versus precision in an experiment. The accuracy is how close the experimental result comes to the accepted or actual value. So if you think about a dartboard, accuracy is represented by how close the darts are to the bullseye, that accepted result. The precision of an experiment is the measure of its reliability, how reproducible the result is. So if I'm throwing darts at a dartboard, it's how close those darts are to each other, how reproducible it is, right? So here are some examples here about low accuracy, low precision, high precision. There is a difference, right? There is a difference. Now, what affects accuracy and precision are errors. So systematic versus random errors. Systematic errors are caused by defects in the measuring instrument or parallax reading of the instrument. So what that means by it's like defects, right? So that would be like an offset. Now, parallax reading means you're not reading the instrument correctly. All right, you're reading it off to one side or the other, and it's going to cause that data to be skewed. It is reproducible when using the same experiment. It shifts the data in one direction, because you're usually, like if you're talking about a scale, it's going to measure 10 pounds heavier every time if that's what the offset is. It cannot be reduced by repeating. You're always going to have that error, but it can be eliminated if discovered. So you could read the instrument correctly, or you could replace the instrument if it's broken. And this leads to poor accuracy. Hey, I'm throwing darts at a dartboard. I'm hitting the same spot, but it's not close to that accepted result. Now, random errors are statistical fluctuations in the measured data by uncontrollable causes in the environment. So it's our inability to take the same measurement in the exact same way. It's not reproducible. It shifts the data in both directions, and it can be reduced by averaging over a large number of observations, and this leads to poor precision, right? Hey, I may be getting close to the bullseye, but my darts aren't hitting as close to each other as I would like them to. So, just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.